I'm Sam Sham of the Idaho National Laboratory. The development of surveillance test articles for surrogate materials surveillance. Acknowledge the support from the Office of Nuclear Energy on this work. Here are the collaborators. Data on materials degradations for advanced reactors during operations are very limited. As illustrated by the figure on the right, the effects of materials degradations from different sources are synergistic, involving irradiation, corrosion, high temperature exposure, and stress. Establishing a surrogate material surveillance program for the management of materials degradations during reactor operation is an important pathway to support the timely licensing of advanced reactors. They will also allow the collection of data on structural materials. The approach to materials surveillance has been pretty much driven by the light water reactor technologies. It is based on the idea of putting surrogate materials in the reactor to receive irradiation dose and then periodically pull them out to perform characterization and mechanical property testing. The surrogate materials are not actively loaded in the reactor. For advanced reactors, we need to figure out how to apply stress to the surveillance test articles during reactor operations. There are two key concepts that will allow us to do that. The first is the SMT test article that Yang-Li Wang developed at ORNL under the ART program to mock up the structural response using a test specimen. It is shown on the left. The second concept is the use of a thermal expansion mismatch within a test article to generate load passively. That led to an initial concept for a passive surveillance test article as shown on the right. It was difficult to find the right combination of thermal expansion mismatch that introduces a tensile load in the test section of the test article. To overcome that, we developed a slightly different design as shown in the sketches. So let the test material be 316H stainless steel. We can weld 316H with alloy 617, which has a smaller coefficient of thermal expansion than 316H. When both bars are free of each other, there will not be any stresses generated when the temperature is increased. But when we join the two bars together and increase the temperature, tensile stress will be developed at the 316H test section. This is how we generate gravity loading passively when such a test article is subject to a thermal transients. We fabricated a test article with 316H as the test material and alloy 617 as the driver material. A proof of concept thermal cycling test was performed, and we demonstrated the viability of this approach. To set the stage for a more detailed picture of the reactor components, I'm showing the Mark I pebble bed FHR design from UC Berkeley. So the reactor vessel and cavity are shown on the left, and some heat transport system is shown on the right. So the question is, how do we use the test article to surveil a safety-related component? Consider components shown on the left. Say we are interested in the structural integrity of a critical location X1 indicated by the green dot. We want to surveil the material at X1, but using a test article placed at location X2 in the coolant. First, say during the reactor design phase, thermohydraulic analysis of the plant operating transients will lead to the temperature distribution and its time history in the metal and in the coolant. Say the thermal cycles at X1 is T of X1, and thermal cycles at the location X2 is T of X2. So the thermal cycles at X1 will generate stabilized cyclic stresses, sigma sub ij, and also strains epsilon sub ij. But if we convert the three-dimensional stresses using effective quantities like effective stress and effective strains, the stress-strain hysteresis loop can be parameterized by a number of parameters as shown in the sketch on the lower left corner. So the question is, can the test article geometry be optimized so that the hysteresis loop of the material at X1 can be reproduced by the test article due to the thermal cycles at X2? So this is what we really want to be able to do. So here's the answer. Due to the limited number of adjustable dimensions of the test article that can be optimized, we can capture two key parameters from the hysteresis loop that we are interested in. We have chosen the strain range, delta epsilon, and the elastic fallout factor Q that is related to the slope of the stress relaxation path by the equation shown, which is the Q, the elastic fallout factor, is equal to 1 minus the Young's modulus divided by the slope. So the strain range provides a measure of the cyclic response, and the fallout factor characterizes the structural response. We developed a test article sizing app for such an optimization. So given the mechanical hysteresis at X1 and the thermal cycles at X2, the app can determine the test article dimensions so that it can match the target strain range and the target elastic fallout factor. We can also place constraints on the dimensions of the test article before the optimization. For example, we can limit the length of the test articles to, say, 3 inches long. We have designed two families of passively loaded test articles. One set is 12 inches long and the other 3 inches long. For each set, we have a tapered design and a step design for the transition of the diameters for the inner test rod. We can put strain gauges on the 12-inch long test articles, but not the 3-inch ones. This is how the test articles are fabricated. The process is the same for the large and the small test articles. We use alloy 617 and 316H bar stock. Then they are welded together by friction stir welding. The inner test piece and the outer casing are machined to dimensions. And finally, the inner piece is inserted into the outer casing, and the ends are welded together using the E-beam welding. And a completed test article is shown on figure 5. We have started long-term thermal cycling tests of 4 12-inch test articles and 3 3-inch long test articles. They all have thermocouples attached. The large ones have strain gauges. For the small ones, we just use the slot in the casing for visual inspection. Here are the recorded temperature histories from all the test articles. And in the bottom row, the strain histories from the large ones. We heat up the furnace at a prescribed rate. When the upper temperature is reached, we turn off the furnace and the temperature drops gradually. The temperature cycle period is about 200 minutes, so 3.3 hours. We did have a strain gauge problems. One failed during the test and it was replaced. The thermal cycling test is ongoing. Well, here are what we will be doing in fiscal 2022. We will continue the thermal cycling tests until failure. Last year, we started a fabrication task to replace alloy 617 by moly TZM as the driver material in order to provide more flexibility on the strain ranges. We'll complete the task in fiscal 22. We will develop a protocol for controlled temperature cycling. In the tests that are currently being done, we don't have a very good control in terms of how the cooling rate of the specimens. So we would like to be able to control that by developing other control protocol. We also want to reduce the size of the small test article for practical deployment. Currently, 3-inch long test articles to be placed in the reactor to receive all the dose would be too large. So we would like to get down to maybe 1.5 inch or even 1 inch long. So fabrication will be a challenge. And also, we will explore string measurement methods for the small test article in order to generate validation data. So the challenges in the string measurements are, well, the small size. For the small test article, the test section, the diameter is about 1/10 of an inch, so it's very small. And if we shrink the test article from 3 inch to smaller, that diameter is even smaller. And also that the test section has a curved surface and the temperature is high. ORNL, together with Boise State, have been developing printed strain gauges under the Advanced Sensors and Instrumentation Program that will address these issues and allow real-time strain measurement. We will leverage the ASI development for the ORNL MSR work. Lastly, I would like to point out that we have a parallel effort by the Advanced Reactors or Regulatory Development Program. The task is led by Jason Christensen of ORNL. The work is to produce a guided document that will present regulatory options to leverage the material surveillance technology being developed by the ART program for advanced non-LWR industry stakeholders to review and endorse. Some example options are develop and implement a materials degradation management program that will provide early warnings on structural degradation and on impending structural failure of a structure of safety-related components, or develop a strategy for the advanced non-LWR industry to balance and potentially reduce part of the upfront new materials data requirements from ongoing long-term materials testing. So with that, I thank you. That's the end of my presentation.